In the beginning, the quest to understand our cosmic origins. Humanity has always marveled at the night sky, wondering about the vast, dark expanse and its dazzling lights. For millennia, people told stories of creation and cosmic events to make sense of the universe. But in the last century, science has offered a groundbreaking narrative, the Big Bang. This is the story of how everything we see, the stars, planets, and galaxies, and even space and time itself, began with a single, dramatic event. The journey of discovery began in 1929, when American astronomer Edwin Hubble found that distant galaxies were moving away from us, indicating the universe was expanding. This realization was monumental. By reversing this cosmic expansion in our minds, it became clear that there was a moment, billions of years ago, when all of space was compacted into an extraordinarily hot, dense state. This early universe, almost 14 billion years ago, exploded outward, kicking off an epic expansion that has never ceased. The early universe, a cauldron of creation. Immediately following the Big Bang, the universe was a chaotic and intense environment. In less than a fraction of a second, it expanded at a rate far beyond the speed of light, with temperatures and energy densities unlike anything we can imagine today. Theories suggest that the universe grew from the size of a subatomic particle to something as large as a galaxy in mere moments. This phase, known as cosmic inflation, set the stage for everything that would follow. The universe was, at this point, unrecognizable. In the first few minutes after the Big Bang, it was far too hot and energetic for atoms to form. Instead, it was filled with a scorching, primordial soup of particles, including quarks and gluons, the building blocks of matter, which swirled and collided in this early cosmic fireball. These particles were so energized that they couldn't bind together in stable forms, but this era laid the groundwork for the universe's eventual structure. As the universe cooled slightly, quarks began to bind together, forming protons and neutrons in a process known as quark confinement. These protons and neutrons became the foundation of atomic nuclei, setting the stage for the birth of elements. The cosmic microwave background. An afterglow of creation, one of the most compelling pieces of evidence for the Big Bang, came in 1964 when Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background radiation, CMB. This faint radiation, detected in every direction in space, is an echo of the Big Bang, a remnant of the early universe's heat. At around 380,000 years old, the universe had cooled enough for atoms to form, allowing photons, particles of light, to travel freely through space for the first time. These photons have stretched into microwaves due to the expanding universe, giving us a glimpse into a young cosmos. Penzias and Wilson's discovery provided irrefutable evidence that the universe had a hot and dense beginning. The CMB allowed scientists to see back in time, capturing an era when the universe was only 380,000 years old, a baby in cosmic terms. The discovery earned them the Nobel Prize in 1978 and remains one of the pillars supporting the Big Bang theory. Particle accelerators, windows into the Big Bang. To understand the conditions of the early universe, scientists have turned to particle accelerators like the Large Hadron Collider, LHC, at CERN. These powerful machines smash particles together at nearly the speed of light, recreating conditions similar to those just after the Big Bang. By studying these collisions, scientists can observe high-energy phenomena and better understand how the four fundamental forces of physics, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, behaved in the universe's infancy. One of the most critical moments in cosmic history occurred within billionths of a second after the Big Bang, the breakdown of electro-weak unification. At this stage, electromagnetism and the weak nuclear force, which were once unified, separated. This division allowed particles to gain mass and marked a turning point in the evolution of the universe. The LHC experiments have helped scientists probe these early conditions, though the mystery of the singularity itself, the moment of the Big Bang, remains unsolved. From chaos to structure, the formation of matter. A few millionths of a second after the Big Bang, the universe had cooled enough for quarks and gluons to combine, forming protons and neutrons in a process called quark confinement. This period was fleeting, But it was crucial. It established the building blocks of all matter we observe today. As the universe continued to expand and cool, protons and neutrons clumped together to form atomic nuclei in a process known as Big Bang nucleosynthesis. This process created the lightest elements, primarily hydrogen and helium, along with trace amounts of lithium. These primordial elements make up most of the visible matter in the universe today. Nuclear fusion reactions, much like those that power our sun, combine these particles into nuclei, marking the first steps toward complexity in the cosmos. However, any heavier elements would have to wait billions of years until the formation of stars to come into existence. In this early universe, energy levels were so high that the atomic nuclei formed were fragile. High-energy photons destroyed most nuclei almost as quickly as they formed, a process known as photodisintegration. But as the universe expanded and cooled further, this destructive process slowed and more stable atoms could emerge. Enter the stars, the first light of the universe. After hundreds of millions of years of darkness, the universe was ready for the next stage, the birth of stars. These early stars ignited the first light, kickstarting the process of star formation and galaxy evolution. Gravity pulled hydrogen and helium gas together, forming dense clouds that eventually collapsed under their own weight, triggering nuclear fusion and giving rise to the first stars. These ancient stars, massive and short-lived, forged heavier elements in their cores, elements necessary for planets, moons, and eventually life itself. When these stars exhausted their fuel, they exploded in supernovae, scattering their enriched guts across space and seeding the cosmos with the materials needed for the next generation of stars and galaxies. Over billions of years, these generations of stars and supernova explosions helped create the elements that make up our solar system, Earth, and everything on it, including us. The singularity, the question. Science can't yet answer. Rewinding time to the Big Bang, we arrive at a cosmic paradox. As we approach the Big Bang itself, distances shrink to zero, and energy density rises to infinity. Here our mathematical models break down, leading to what physicists call a singularity. This is a point where our understanding of space, time, and the laws of physics collapses. In the heart of a black hole, or at the birth of the universe, the equations of general relativity give nonsensical answers, filled with infinities and zeros. This is where Albert Einstein's general relativity reaches its limits. General relativity describes space-time as a smooth fabric, which curves in response to mass and energy, giving rise to gravity. But at the singularity, space-time is anything but smooth. It twists and warps into chaotic structures that defy conventional physics, a state that scientists sometimes refer to as space-time foam. In this bizarre realm of space-time foam, classical physics no longer applies. Instead, gravity would need to be explained through the lens of quantum mechanics, a probabilistic theory that governs the subatomic world. In the quantum domain, outcomes are not deterministic. They exist as probabilities. This shift challenges our understanding of causality, as time itself loses its usual structure, becoming something chaotic and unpredictable. Quantum gravity, the search for the theory of everything. One of the biggest mysteries of modern science is how to merge general relativity, which describes large-scale phenomena like planets and galaxies, with quantum mechanics, which governs the microscopic world of atoms and particles. The answer lies in a theory of quantum gravity, an elusive concept that would describe gravity in quantum terms. Such a theory might help explain what happened at the Big Bang and within black holes, where both quantum effects and intense gravitational forces are at play. Two leading candidates for a theory of quantum gravity are loop quantum gravity and string theory. Loop quantum gravity attempts to describe space-time as a network of discrete loops, while string theory proposes that all particles are tiny vibrating strings in higher dimensional space. Both theories offer promising insights, yet neither has provided a complete answer to the singularity problem. Cosmic inflation, the theory that gave the Big Bang. Its bang in 1980, physicists Alan Guth and Alexei Starobinsky proposed the theory of cosmic inflation to address some of the Big Bang's puzzles. Inflation suggests that, in a fraction of a second, the universe underwent an exponential expansion, smoothing out its structure and explaining why the cosmos appears so uniform. This rapid expansion also froze quantum fluctuations in place, which later became the seeds for galaxies and galaxy clusters. Cosmic inflation helps explain the uniformity we observe in the cosmic microwave background radiation, supporting the idea that the Big Bang was not a random explosion, but a calculated expansion that set the stage for everything that followed. Today, observations of the CMB align closely with inflation's predictions, making it a cornerstone of modern cosmology. The present universe and the mystery of dark energy. Our universe's expansion is still ongoing, but astronomers made a surprising discovery in the late 1990s. The expansion rate is accelerating. This phenomenon, attributed to a mysterious force called dark energy, suggests the universe's fate may be different than we once imagined. Rather than slowing down and collapsing back on itself, the universe may expand forever, growing colder and emptier as galaxies drift further apart. This expansion aligns with inflation theory, showing that the universe has undergone accelerated growth not just once but at least twice in its history. Yet dark energy remains enigmatic, and scientists are only beginning to uncover its secrets. The unanswered questions. As we stand on the brink of new discoveries, some questions linger, tantalizing and elusive. What sparked the Big Bang? Was there a before? What is dark energy, and how will it shape the universe's fate? These mysteries drive scientists to explore, using tools like particle accelerators, powerful telescopes, and mathematical models to probe deeper into the unknown. Our journey from the Big Bang to today is a testament to human curiosity and our desire to understand the cosmos. The universe, vast and mysterious, has many more stories to tell. Each discovery brings us closer to answering the ultimate questions of existence, even as it reveals new wonders to explore.